Okay, here are the results we got when we did the Tower of Hanoi problem by moving the discs on the rings. What we were able to see is when we had one disc, it took one move. When we had two discs, it took 3 moves. When we had 3 discs, it took 7 moves, and so on. And what we're curious about is how many moves it's going to take when we have 64 discs, so that we can answer the question in the puzzle about how long it's going to take these high priests to move all of the discs before the universe ends. But what we need to notice is that these numbers in here match up with the number of moves the previous time. So what you might notice is that we can come up with a recursive formula. If we call this M1, meaning moves, M2 for number of moves with 2 discs, number of moves with 3 discs, number of moves with 4 discs, number of moves with 5 discs, well then 64 is going to be M sub 64. Can we come up with a formula for this thing that talks about the number of moves related to the number of discs? Well, if you look at each one of these things, each time it's based upon the number of moves when you had one less disc, then we add one more, and then we do the number of moves from the previous one again. So the number of moves based upon the number of discs is going to be 2 times the number of moves the one before plus 1. What we have here is a recursive formula. So our recursive formula is that M sub D is equal to 2 times M sub D minus 1 plus 1, provided that we have an initial starting point of M sub 1 equal to 1. We have a recursive formula, and it'd be easy to write a computer program with this formula in it, pass it a 64, and see what the result is. It would have to go through calling that function 64 different times to be able to come up with a number, and that's a common programming exercise that we could have. Of course, you can see here if we wanted to figure this out for any number of discs, what we're looking at is just doing this formula for n. But wait a minute. Isn't there another way we could think about this? Look at these numbers. You might see a bit of a pattern here. You see, this thing, these numbers are just a little short of perfect squares, right? Because you see 4, 8, 16, 32, 2. They're perfect squares. It's always 1 less than that. Or another way to, that's one easy way to think of it. Or if we want to think of it, we can think of here, this one is, instead of thinking of it as 2 minus 1, this one is 2 squared minus 1. This one is 2 to the first minus 1. This one is 2 to the third minus 1. This is 2 to the fourth minus 1. This is 2 to the fifth minus 1. So it might be natural to think that M sub 64 is going to be 2 to the 64th minus 1. And if we wanted to figure this out for any old n, here, 64 is going to be M sub 64 is 2 to the 64th minus 1. And to do it in general, then that would be saying for any n that you put in here, m sub n is 2 to the n minus 1. While we've done a recursive formula over here, what we're calculating here when we say m sub d is equal to 2 to the d minus 1 is we are figuring out an explicit formula. Well, we've spotted a pattern, but we haven't proven yet that that's really the right pattern. We'll have to do that, and we'll do that in the next video. But before we do, let's look at this number over here of 2 to the 64th minus 1. 2 to the 64th is a big number. Just did that on my calculator. So 2 to the 64th is approximately 1.8 times 10 to the 19th. Suppose those priests were moving the discs once a second. Pretty fast for moving all these discs. It was a lot faster than I was moving them on the previous video. Well, how long is that number of seconds? That's a long time. You could go through and divide it by 60 to figure out how many minutes it is, and do all the math, turning the seconds into minutes, into hours, into days, into years, into centuries, and you discover it's a very, very long time. I might also direct your attention to some things dealing with big numbers. It's in section 5.7. There's a table, about 2/3 of the way down the page, that looks at some numbers. And you see that 10 to the 7th is basically the number of seconds in a year. And if you look, 10 to the 17th is listed as the age of the universe in seconds according to at least one theory. Well, that means if they were moving these things once a second, it would take longer than the age of the universe. I think we're in pretty good shape. But wait a minute, what if we had a computer do this? What if we had a computer? I mean, a computer could generate the output of this stuff very quickly. It could do, instead of moving the disks physically, it could move them electronically, say, 100 times a second or 1,000 times a second. Well, how about a gigasecond? A gig of these disks every second. Well, try calculating how long it would take for a computer program to go through all of these things if it's doing a gig of these calculations every second. Even if you divide this number by a gig, you get a huge number that you can see is going to be many, many years. And if your computer science teacher asked you to do a printout of all the combinations, well, you see that would be an impossible assignment. Well, okay, we have two formulas here describing the Tower of Hanoi, a recursive formula and an explicit formula. But we've just sort of come up with them. How do we know that this explicit formula really works? That looks like a job for mathematical induction.